Hello, AP Stat students. So, last time you learned about getting the best type of sample. So, now that we have our sample, what do we do? This is statistical studies. So, there are two types of studies that I mentioned at the start of this chapter. There are observational studies and there are experiments. Observational studies do not seek to influence or affect results of a study, whereas experiments impose a treatment upon individuals to determine if the treatment may cause some sort of effect. So, observational studies are like your sample surveys where you call someone, you ask questions to get their opinions, or you watch things to get some information about. Experiments do influence a result. Oops. And basically, the experiments imposing a treatment, we want to determine if the treatment may cause some sort of an effect. Therefore, to establish cause and effect, the causation, an experiment is the only source of convincing data. However, with experiments come the fact that most people are going to volunteer. So it must most involve a voluntary response. So, and that is bad sampling. And with bad sampling, we can't infer to the population, but we can establish that cause and effect. In any statistical study, there are variables. And we mentioned these when we talked about scatter plots. A response variable measures the outcome of a study. An explanatory variable may help explain or influence changes in a response variable. In a statistical study, there could also be a lurking variable. So here's a new type of variable I haven't mentioned before. A lurking variable is a variable that is not among the explanatory or response variables in a study, but that may influence the response variable. Lurking variables make it hard to see the relationship between the explanatory and response variables. Since observational studies do not influence what is happening in the study, there can be lurking variables that can mask a true cause and effect. Experiments, however, if by design, isolate variables so lurking variables are minimized. Lurking variables are never really eliminated, and the whole goal is to make sure that their effects are minimized. All right. Another vocabulary word is confounding. Confounding occurs when a lurking variable and an explanatory variable are associated in such a way that their effects on the response variable cannot be distinguished from each other. I put additional notes after this section that I highly recommend that you read. And a lot of times you'll get that additional information, and that is just not anything for a grade, but that's something that's going to benefit you and that'll help you do better. When analyzing a study for confounding variables, be sure to explain how it's associated to the explanatory variable and how it could be or how it could affect the response variable. Another good resource is going to your AP class site, and hopefully you've signed up for it because That's just additional practice that we are not allowed to grade, and if you wanted to do any of the work and there's videos over each lesson, I highly recommend it, especially if a chapter is hard for you, that's what I would do. Here's a sample problem. Does eating dinner with their families improve academic performance? According to an ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades in school. This finding was based on a sample survey at Columbia University. Was this an observational study or an experiment? And you can get your answer in the last sentence. Because findings were from a sample survey, this is an observational study from a sample survey. And no treatment was imposed. What are the explanatory and response variables? So basically, the first question just kind of tells you what the variables are. Does eating dinner with their families improve academic performance? So the explanatory variable is the number of times or number of nights. Guess we could have said just days. So number of nights eating dinner with family. And dinner's a nighttime activity. And the response variable was grade point average or academic performance, all measurable. Explain why this study cannot establish a cause and effect relationship. Suggest a lurking variable that may be confounded. So remember, observational studies cannot establish a cause and effect because they don't seek to um, influence the results of a study. All right, there's lots of lurking variables here. And remember, lurking variables are not among the explanatory variables. So in this case, explanatory variable was number of nights eating dinner with family. So lurking variables in this list is not complete. Obviously, I'm just going to put a couple. You can add some more to it if you want. You could have more involved parents. And when you have more involved parents who spend time with their teens, oops, their patterns, they tend to help boost that academic performance because they ask questions, they're involved. So that's one. Another one just could be better nutrition, eating dinner with their family every night, getting that proper nutrition, getting the blood flow to the brain, affecting your GPA. So these are additional variables that need to be considered. And that's a sample where example where you know the difference between observational study and experiment. We mentioned the explanatory response variable and mentioned lurking variables. All right. Next part is talking about the other type of statistical study, and that's the experiment. So, experiment has its own language. A specific condition applied to the individuals in the experiment is called a treatment. So, a treatment is imposed. What kind of treatment? There can be lots of kinds of treatment. If an experiment has several explanatory variables, a treatment is going to be a combination of specific values of these variables. And we'll do an example problem, so you'll see a combination. The experimental units are the smallest collection of individuals to which treatments are applied. I know on your next test you'll be given an example problem and you have to identify what the experimental units are, what are the variables, what are the treatments. And it's kind of like a thing that you will get asked on AP exams as well. When the individuals are human beings, they are often called subjects, but in many textbooks, I've also seen that subjects can be um, animals, they can be plants. I mean, they can be other things, but so that they call that subjects, but some books just say if they're humans, they're often called subjects. Okay, let's look at our first example in which we have to identify the experimental units, the explanatory and response variables, and the treatments. So we will do two examples like this. A study, this is called a lousy situation. A study published in the New England Journal of Medicine, March 11th, 2010, compared two medicines to treat head lice, an oral medication called ivermectin and a topical lotion containing malathion. Researchers studied 812 people in 376 households in 7 areas around the world. Of the 185 households randomly assigned to ivermectin, 171 were free from head lice after 2 weeks, compared to the only 151 of the 191 households randomly assigned to malathion. So here we're asked to identify the experimental unit. So in this particular case, you would think that there are 812 people, what have you, but honestly, what it is with lice, it's when if one person gets it, it tends to be where everybody gets it, or at least more than one person in the family. So households are the experimental units. So in this case, the 370, so the whole household is being treated. So the 376 households are your experimental units. The entire households were assigned to treatments. The explanatory variable is the type of medication, so either it was an oral or topical lotion. So that's the type, the amount and type, I guess, or type. The response variable is so what was being measured? Either there was head lice or there was no head lice. And the treatments, the actual treatments that were being imposed were ivermectin and or malathion. Okay, let's do another example. This one's called growing tomatoes. Does adding fertilizer affect the productivity of tomato plants? So right there, you have kind of um, information on the variables. How about the amount of water? Well, there's more given to the plants. To answer these questions, a gardener plants 24 similar tomato plants in identical plots in his greenhouse. He will add fertilizer to the soil in half of the pots. Also, he will water 8 of the plants with half gallons of water per day, 8 of the plants with 1 gallon of water per day, and the remaining 8 plants with 1.5 gallons of water per day. At the end of 3 months, he will record the total weight of tomatoes produced on each plant. So your productivity is going to be the total weight of the tomatoes. And then you have some of those variables listed too, and there's more than one. So let's start with the experimental units. The experimental units in this problem are your 24 similar tomato plants. Be specific in the context of the problem. Don't just call it like 24 plants. The explanatory variables, there's two. The first one was whether there was fertilizer applied or not, and the second one was the amount of water. So, right, and your response variable was the weight of the tomatoes produced on each plant. Okay, lastly, this one is going to take a little time because of the splitting of half the tomatoes with fertilizer and then all the tomatoes getting a specific amount of water. So there's actually 6 treatments, and you do have to list all 6. You have to be specific. So I will do that. Move that out of the way. So remember, the first one is, so let's do the 3 that have fertilizer, because half the plants had fertilizer in them. So okay, so you had fertilizer with half a gallon of water. You had fertilizer with 1 gallon, and you had a fertilizer with 1.5 gallon. And then the other half did not have fertilizer, so those can be your treatments 4, 5, and 6. So no fertilizer, half a gallon water, no fertilizer. You can abbreviate too if you want. These are your notes. 1 gallon water, and no fertilizer, 1.5 gallon water. So there's 2 sample examples where you had to identify the vocabulary relating to experiments. Okay, now let's go ahead and talk about bad experiments. So bad experiments won't take into consideration lurking variables and minimizing them. And the example we're going to do is going to talk about that. This example is called Does Caffeine Affect Pulse Rate? Many students regularly consume caffeine to help them stay alert. Thus, it seems plausible that taking caffeine might increase an individual's pulse rate. Is this true? Well, one way to investigate this is to have volunteers measure their pulse rates, drink some cola with caffeine, measure their pulse rates again after 10 minutes, and calculate the increase in pulse rate. Unfortunately, even if every student's pulse rate went up, we couldn't attribute the increase to caffeine. Perhaps the excitement of just being in an experiment made their pulse rates increase, or perhaps it was the sugar in the soda and not the caffeine. Or perhaps their teacher told them a funny joke during the 10-minute waiting period and made everyone laugh. Or maybe someone like farted in class and everybody's laughing, yada, yada. And so their pulse rate was higher for that reason. In other words, there are many lurking variables that are potentially confounded with caffeine. And then you're not going to be able to say that caffeine affects pulse rate. So, to minimize lurking variables, we try to make sure the groups receiving treatments are as similar as possible. So, the only systematic difference is the treatment. This allows us to be more confident that the results are caused by the treatment. So, a better way that we could do this is just you need more comparison. So, to rectify this, we could do split our classes up. We could do a say a third of the class with have them drink soda with caffeine, a third drink soda without caffeine, and then having like a third of the class drink soda that's sugar free and caffeine free, and then compare the results. And that comparing the actual results is something we're going to do in second semester when we do the statistical studies comparison and come up with inference. So right now we're just thinking more along the lines of sampling and experiments and what are good. The next thing, and this is super duper important, and if you have a textbook, it's page 240 to 247. And it's in our textbook, it's called Completely Randomized Design and the parts of it. But in other textbooks, it's the same basic principles and it's called Randomized Comparative Experiment. This little topic has so many multiple choice questions that could come from it. I would really start this entire thing. So the principles of good design there's three of them. So the first one, so they have to be comparative, random assignment, and replication. So a proper comparative design ensures that influences other than the experimental treatments operate equally on all groups. And that's why I put in additional notes and reading that you can do, and it gives more information. And there's examples too, so you can look at those examples. This helps with the effects of lurking variables. One group should serve as a control group. So when you're talking about comparison, you're comparing with that control group, which provides a baseline for comparing the effects of the other treatments. An inactive treatment given to a control group is called a placebo. And if you watch the news and stuff and you're reading about studies, they always talk about a placebo was given to this group, and so on. Not all control groups, though, receive inactive treatments. So even though, and I'll mention that when we do our last example, and every group will be given a treatment. So, um, yeah, so you don't have to have a placebo in an experiment for it to be valid. Okay, a random assignment ensures and helps balance out the effects of lurking variables that we can't control or we don't even think of on treatment groups. That is, random assignment forms groups of experimental units that should be similar in all respects. Before the treatments are applied. Methods used to create a simple random sample. Remember, SRS, even though we have that systematic random, the SRS, when I talk about it, is a simple random sample, can be used to randomly assign experimental units to treatments. So, you know what I mentioned with experiments, you have volunteers. So even though you have volunteers, you're going to then assign those volunteers. You don't let them pick randomly to the treatment they're getting. So that is a good example, good principle of experimental design to make sure that they're assigned randomly. Remember that it's extremely important to describe how you are randomly assigning experimental units to treatments. So some of you are very vague and you're not very clear, and you write maybe one sentence that doesn't really fully describe how you randomly assign. You just said, "Hey, I you know, labeled them 1 to 20 and then put the first 5 in groups." You don't really tell, well, how did you randomly assign them? Did you use a random number generator? Did you put the names in a hat and so on? You need to be specific as you're carrying out the experiment. And you might be doing this in the future if you end up doing research, studying in college. So just remember, these are really good things to learn. And if you're going into even business, a lot of people, one of my students a few years ago, he was in my AP stats, a great kid, love him. He asked me, he's like, "Should I take business stats?" I go, "Well, what do you want to do when you go to college in Washington, D.C.?" Because that's where he was going. And he told me what he wanted to do. And I said, "Yeah, you should definitely take business stats." And then I heard from him his freshman year. He's like, "Oh my gosh, what I learned in your class was so useful and it made that class so easy." So, and beneficial because it was to his particular field of study. And the last one is replication. Use enough experimental units in each group so that any differences in the effects of the treatments can be distinguished from the chance differences between the groups. And so, larger samples are always going to give us better results as far as inferring to the population. So, if you're like 60 people is better than 6 people. Now, how large does it have to be? That you're not really, you don't need to worry about it. You just need to know that some, not like something like 4. If you have a choice between 4 and 40, then obviously you want 40. So just can you repeat this over and over again and get similar results? So that's what replication is. So what can go wrong with experiments? um, the placebo effect, a response to this is a response to an inactive treatment, because I mentioned earlier what a placebo was, being given an inactive treatment. We can avoid this by using a blind study. And there are two types. There's what is called a single blind study and a double blind study. In a single blind study, the subjects do not know which treatment they are receiving. So when talking about that cola soda example, cola, whatever, um, if you have the groups in the thirds and one group is getting soda with caffeine, one's getting soda without caffeine, um, and one's getting soda with that's sugar free and no caffeine, they don't know. They just know that they're being given a soda and they're drinking it. So that's where the subjects don't know what they're getting. That would be a single blind study. In a double blind study, the subjects and the people interacting with the subjects do not know which treatment they are receiving. So, in this particular case, if there's a person there to hand out the sodas, that person doesn't know um, what each group is getting. That person's just handing that out. So, in that particular case, um, neither the subjects nor the people know which treatment they are receiving. And that brings us to our last example. And this is going back to the caffeine affecting pulse rate. So, won't read it to you, but um, because we already read it to you before. In this particular problem, we are asked to create an outline to show how to put together a good experiment that meets the principles of experimental design. So, and the one thing I'm going to change to make this really easy as far as division goes is let's call it 21 volunteers, right? Okay, so we have 21 volunteers. And remember, we want to randomly assign them. So we want to explain that before we draw our outline. So we could write it right here. We can randomly, and when you're asked to do this on your homework, follow this guideline. So randomly assign, since there's 21 two-digit numbers to each person. So I would do like 01 to 21. Then use a random number generator, and abbreviate, to choose groups. Or you can say, hey, I assigned numbers 1 through 21 to each person, and then I used my graphing calculator and used random integer to select um, my groups that way. But this is, I mean, then, the first 5 numbers would go here for next, or first 7, sorry, since there's going to be 3 groups. I would do 3 groups because there's 21 and you divide, it not divides nicely. So here, you're going to have part of your outline, 3 groups. You have group 1, group 2, and group 3. And you already said that they were randomly assigned. So group 1, and then write down what treatment they're getting. So group 1 would be soda with caffeine. Group 2 would be soda without caffeine. Oops. And the last one would be soda that's sugar-free and no caffeine. That could be your control group. A control group that's still getting soda, okay, but no. Okay, and then you would measure their response would be measuring the pulse rate. And then later on, semester 2, we would compare the data. You don't have to do that in this particular chapter. You're just designing it. That's one way of having a good design. A second way of making sure you have a really good experimental design is you could have measured their pulse ahead of time. So we don't have to redo it and make another outline. You can just say you can measure their pulse beforehand and then assign to the groups. And that would work as well. And that is an example of a good experimental design. That is it for our notes for 4.2a. Have a great day, stat students.